Hello, my name is Cadet Paul, and I chose to do my systems thinking video assignment on the Fukushima Daiichi nuclear disaster, one of the two worst nuclear disasters in history of the commercial nuclear energy program. For some background to the disaster itself and the precursor to the actual nuclear meltdown and system failure, you can see that there was a magnitude 9 earthquake at 2:46 p.m. on the 11th of March 2011 and killed approximately 19,000 people. The earthquake was not the main source of damage or deaths. It was the subsequent 15-meter tsunami that hit most of the eastern seaboard of Japan. As you can see, the epicenter of the earthquake and therefore the tsunami was very, very close to the Fukushima number 1 site. That is where the nuclear meltdown occurred, and obviously felt the brunt of the force of the tsunami. Here is a diagram of the reactors that were used at the Fukushima Daiichi plant. This reactor is a boiling water reactor, which is a type of reactor that I'll get into later on in the presentation, but I wanted to jump into the system failure portion of the presentation, just so when I describe how a reactor works, you can understand how this would cause system failure. The red generator that you see on that second level is actually in what's considered the basement. When the tsunami hit, it actually flooded the basement, destroying the electronics and flooding the generator. The generator is the source of the pump for the heat transfer system in these boiling water reactors. Without the heat transfer system, the water evaporates, leaving exposed fuel rods, and exposed fuel rods then heat up to incredible temperatures, up to 2,300 degrees Celsius, and cause a melting. That slag that's created is called chromium, and that chromium melted through what you see there is the reactor vessel, that silver pod, and then the chromium hit the floor. The yellow is a steel liner that is around the reactor vessel. Now, we as the public don't know how far that chromium went, how deep it went into the ground, whether it pierced the steel barrier, but we know that it is incredibly hot and incredibly radioactive, and because of the tsunami, the 15-meter waves, it flooded and destroyed the heat transfer system, which then caused a reactor meltdown.
Fukushima reactors have a different technology than the pressurized water reactors built by the French operator EDF. They are boiling water reactors, called BWRs. We say reactor because the heat in the core is produced by fission reactions. Boiling water because the water that removes the heat from the core turns into steam, and the steam goes directly to the turbine. The turbine drives the generator that produces electricity. Afterwards, the steam is condensed with the help of a seawater cooling system and returns to the core. A boiling water reactor has only one single system combining feed water and steam. The core is composed of fuel assemblies containing uranium. It is controlled by control rods introduced from the bottom that can stop the fission reactions in case of an emergency. Fission of uranium nuclei produces radioactive atoms that in turn produce heat, and this continues to occur even after reactor shutdown. This is called residual heat. Keeping the fuel confined and cooled is a major safety issue. The fuel is isolated from the environment by different containment barriers, just like the famous Russian dolls. A first barrier, the fuel cladding of zirconium alloy. A second barrier, the steel reactor vessel in combination with steam and water cooling systems. Finally, the third barrier, the containment building in concrete with a leak-tight steel liner. The fuel is kept under water in the reactor as well as in the adjacent pool where the spent fuel is unloaded. The pool is located at the top of the reactor vessel to facilitate the transfer of fuel underwater.
Now that you have a better understanding of how the boiling water reactors that were used in the Fukushima Daiichi plant, we can go into the systems thinking portion of the presentation, how the system is classified, and then understanding the systemogram that outlines how the system operates. So classification, obviously a reactor is physical. For system visibility and the structure of the system, there are two separate instances as well. The structure is closed, aka the fission, where inside the reactor core there is a closed system of control, slowing down neutrons and making sure that the chain reaction is not too volatile while still maintaining energy efficiency. However, the heat transfer system, as described in the video, is open, where it uses the seawater on the coastline to then transfer the heat, the residual heat, as they were describing, uses the outside seawater to cool it, and then takes in the condensed air that was used. It is an open system in that regard. The visibility, we understand boiling water reactors as they have been in use and developed since the late 60s. So it would be a white box. We understand the technology. We can dissect everything inside a nuclear reactor. However, TEPCO, the organization that ran the Fukushima plants and ran the subsequent investigation, we don't have the full picture because they were the only organization to conduct the investigation. We don't fully understand what's going on inside now, how deep the chromium has gone, a lot of the investigations into what radiation leakage there was, etc. Spatial arrangement. So the metasystem is the power plant itself. The subsystems, there's the reactor and the control room. Control room being where the operators and engineers monitor and control the nuclear power output. The reactor contains the core, which is the fuel and control rods, and the reactor also is part of the heat transfer system. Both of those work simultaneously to help the reactor element function properly. The evolution of nuclear power and subsequent important safety evolutions and adaptations started with Generation 1 reactors very, very early on, post-Manhattan Project and post-nuclear warfare. We saw in 1954 the technology being utilized for power in the U.S. Army and Navy. They both had the first successful nuclear programs. Then in 1956 in England, the first commercial nuclear power plant generated 50 mega electron volts of energy. This is important to realize because now we are generating electric power from these nuclear power plants in the gigawatts. It is exponentially increased the power output, and that has been because of the evolution, as you can see from the early prototypes, to Generation 2, which is where Fukushima as well as the Chernobyl reactors fall under, both boiling water reactors. Generation 3, advanced light water reactors, where instead of using heavy water as the cooling agent for the pools, you use light water, which is more efficient but was more technologically advanced and needed more research. The system need, we saw the advantageous importance of nuclear power and controlling it from the weapons phase to the commercial energy phase. Commercial energy being able to propel ships and submarines, as well as being able to utilize the energy output commercially for homes. The developing concept, creating reactors and designing the systems that could then be take it from the weaponization phase to commercial, produce the system, create those initial power plants in 1956 and 57 in the UK and the US, deploy the system, starting to use Generation 2 reactors that were actually becoming economically efficient in creating energy, better technology and better safety research in PWRs and BWRs, and then the operational phase as they are in now. The Fukushima reactor was in the operational phase and still had years of life left, but was sort of forcibly put into retirement by the Fukushima nuclear disaster. The risk that was associated at each phase was obviously the risk of nuclear disaster, the risk of radiation and fallout. However, adaptation through each generation was less prone to meltdown through stronger materials, through more safety systems, through better research, as well as international standards being set by the International Atomic Energy Association. With these advances, the nuclear power industry is hoping to revolutionize with faster reactors, more advanced reactors, as well as looking into fusion, which creates less radioactive byproducts and a tremendous amount more energy.